So welcome everyone to the RRI colloquium today on the topic quantum information. Today actually is a national holiday in India. And I'm really glad to see so many enthusiastic participants already at our event. Before I go on to the speaker introduction, let me take this opportunity to mention that our today's colloquium is also a part of events being organized globally to mark the launch of a World Quantum Day on April 14th. The official launch happened just about an hour ago, and events are happening as we speak in different time zones. The World Quantum Day aims at promoting the public understanding of quantum science and technology around the world. It is a decentralized and bottom-up initiative inviting all quantum scientists, engineers, entrepreneurs, educators, communicators, and organizations to promote their own activities, such as outreach talks, lab tours, debates, interviews, etc., to celebrate the World Quantum Day at a global scale. A handful of events in different continents on 14th April 2021, which is of course today, will mark the countdown towards the first global celebration on 14th April 2022. This is one among such handful events worldwide. Professor Arun Pati of HRI Allahabad and I are the country representatives for the World Quantum Day from India. Well, we are very glad that today we have Professor Charlie Bennett as our colloquium speaker. Sometimes introductions are necessary, but in case of today's speaker, he really does not need one. I mean, to the quantum community, I would say he's one of our living legends. However, the RRI colloquium series actually has a very diverse audience, and we have people from condensed matter, astro, many people are joining in here and across sciences. And so for the sake of completeness, Charlie, let me present a short introduction. Born in 1943, Charles H. Bennett is the son of music teachers. He got his BS in chemistry from Brandeis University in 1965, his PhD in chemical physics from Harvard in 1971, did a postdoc under the late Anisur Rahman at Argonne National Lab in 1971-72, and has been a research staff member at IBM's T.J. Watson Center since 1973. He is best known for his work on the physics of information processing, including the thermodynamics of computation, the Maxwell's Demon problem, quantum cryptography, quantum computing, quantum channel capacity, and entanglement-assisted communication, including the quantum reverse Shannon theorem. Lately, he has become interested in the applications of quantum information and computational complexity theory to cosmology. He's an IBM fellow, a fellow of the American Physical Society, a member of the US National Academy of Sciences, and a recipient of the Rank Prize, Harvey Prize, Okawa Prize, ICTP Dirac Medal, Wolf Prize, Shannon Award, and BBVA Frontiers of Knowledge Award. On a personal front, perhaps my most recent interaction with Charles Bennett was at the conference at SN Bose National Center for Basic Sciences in early 2018. It was a physical conference. Among many stimulating physics discussions, there was also a wonderful trip organized to a local art gallery. I don't know whether you remember this, Charlie, which remains very special, especially to witness this remarkably keen interest and knowledge that Charlie has in diverse topics over and above physics and mathematics. So on this note, I present to you Charles H. Bennett, who will speak to us about quantum information. So I'll stop sharing my screen, Charlie, and you can share yours. Yeah, thank you.
Well, it's very good to be, so to speak, back. I remember, I think this was my first visit to the Raman Research Institute back about 19 years ago. And it was a very beautiful place, and I think I'm told it still is. So this is what I'm going to be talking about today, the quantum nature of information. And in a way, it's about the quantum ideas and how important it is for it to be part of a general education, not just for scientists and not just for specialists. And therefore, this talk, at least some parts of it, are intended to be accessible to a lay audience. Unfortunately, quantum phenomena have gotten the reputation of being so strange that no one can understand them. And I'll mention that a little further along the way. But I think the lesson is that we need to cultivate a quantum intuition, both for practical purposes, for learning how to use quantum phenomena, which are over a century old now, and for their value for general education and philosophy, for understanding the nature of the world that we're in. So, like other parts of science, of mathematics, quantum information originated from everyday experiences, or information theory, not quantum information. I'm going to talk quantum information pretty soon enough, but information itself was an idea that matured in the 20th century from two grand abstractions. One was Turing's idea of a notion of computation that was universal and independent of the specific hardware. And an even more revolutionary notion was Shannon's notion in 1948 of the best way to study information is to forget about the meaning of communication. So that sounds like it sounds like a crazy idea, and yet it unlocked the information revolution, which is based on computing and the transmission and storage of information. It's remade the world. It continues to be doing that as we speak now. For example, in the ability to have this kind of virtual conference. Now, these abstractions were so successful that in a way, they narrowed people's view of information and computing to the point where people thought of as purely mathematical notions. And in a way, they are abstractions from everyday experience that threw away a little bit too much physics. And I'll get to that soon. But there was some understanding that the use of a physical analogy for information and information processing was just an approximation. For example, in the 19th century, when the notion of universal computation was gradually being discovered by Babbage, for example, he called his computer a mill, a processor, and the memory of it he called a store. But even classical information is different from a material substance like grain, because it can be copied. Information can flow more efficiently through a network. So we have some red information, or let's say on the left, we have some red commodity that wants to go from the upper left to the lower right, and some green commodity that wants to go from the upper right to the lower left. And the black lines show the paths along which they can travel. Well, you can't do both at the same time if it's a material substance, because there is a traffic jam in the middle of trying to get the two things going through the same pipe at the same time. But if it were information, you just copy the information at each side, do an exclusive OR, and then make two copies of the result of the exclusive OR and send it back to the two sides, and you've achieved your result. So this is an example of the kind of difference between information and stuff. And what became clear in the latter part of the 20th century is that quantum theory, which people didn't think had much to do with information, just had to do with physics and chemistry, where it had such great success. But quantum information reveals additional ways in which information is different from the true information, which is quantum information, is even different from these ideas of information, and it can do even stranger things. And in fact, it wasn't too long after Shannon's paper that the seeds of this quantum revolution were hatched by a person who I was fortunate enough to have as a undergraduate classmate of mine, Stephen Wiesner. Now, he's very averse to publicity, and he wrote a paper in 1968, and he eventually submitted it to the IEEE Information Theory Journal around 1970, but he didn't try very hard to get it published, and they didn't understand it. And he kind of forgot about it, except he cared about it and he told me about it. And in this paper, he already showed how to do things with quantum systems that are of an essentially informational sort, and that can't really even be fitted into the way of thinking about information that we all have as a result of the success of Shannon's information theory. And the two things he discussed were combining two messages into a signal, a physical signal, such that the receiver of the signal could receive either message, but not both. Now, of course, you can't do that with the ordinary information because you just make a copy of it and you decode it to both two different ways. And the other idea was money that is impossible in principle to counterfeit. You can't make copies of it because you can't, well, we'll get to that some more. So this idea sat around for a while, and eventually I was excited about it and told everybody that I met that it was interesting and exciting. And finally, I met a computer scientist, Gilles Brassard, and he got excited about it too and started thinking about it in a computer science way. But let's say if you have to explain to somebody at a dinner party what is quantum information, and you know, sometimes I start talking about Hilbert space and things like that, and I notice that at dinner time, people's eyes tend to, they stop paying attention. So I've found a way of the best way I have of explaining it to a lay audience is to say, well, everybody understands normal information. I don't have to explain that. You all use it every day. It's like the information in a book or in a radio broadcast. But quantum information is different. It's more like the information in a dream. If you try to explain your dream to somebody, it makes you forget your memory of it, and you remember only what you said about it. So it has some of these very slippery seeming psychological properties, but unfortunately, despite the efforts of psychiatrists and psychologists for over a century, there isn't a good quantitative theory of dreams, but there is a good quantitative theory of quantum information. And I'll explain the outlines of it in the simplest form I know how to in the next few minutes. Okay, the central principle of quantum physics, and therefore of quantum information, is that between any two reliably distinguishable states of a physical system, there are other intermediate states that are even in principle not reliably distinguishable from the original ones. And that more precisely, the set of all possible states of a physical system correspond to different directions in space, not ordinarily three-dimensional space, but a space that has as many dimensions as the maximum number of reliably distinguishable states that system has. In other words, a property of a system, of any system, is that it has a maximum number of reliably distinguishable states, and any direction is a possible state in this high dimensional space, or more than one dimensional space, but the two states are reliably distinguishable only if their directions are perpendicular. And a closed quantum system develops in time in exactly such a way as to conserve distinguishability. So what's happening to the states is that they rotate around in space in some way, but never get less, conserving the angles between them. So that's, if you have to put the minimum mathematics to understand quantum mechanics, that's it. Now, this is nicely illustrated by polarized photons, which have two reliably distinguishable states. Then you can choose any two states you want that are perpendicular in direction. For example, horizontal and vertical in these perspective drawings. So I can separate horizontal and vertical polarizations by sending these photons. These green photons are coming along in a properly oriented crystal of some material that is somewhat less than perfectly symmetric in its crystal structure, such as calcium carbonate. When you send them in there, the horizontal photons will go straight through and the vertical ones will be deviated while they're in the crystal. And somewhat surprisingly to anyone who thinks about this, begins thinking about it, you can send photons that are polarized at a different direction in, and instead of getting deviated by an intermediate amount, they behave randomly. And they go through the crystal, and some of them go into the horizontal beam and become horizontal, and the others go into the vertical beam and become vertical. So that means that if we agree beforehand, we're only going to use horizontal and vertical, we can use each of those photons to carry one bit of information reliably. But if you send in a photon of a different angle, they would be randomized. On the other hand, if you rotate the crystal and the detectors by 45 degrees, you can use the left diagonal and right diagonal directions as reliably distinguishable states because they're perpendicular. And the apparatus will reliably distinguish them, but it can no longer distinguish vertically from horizontal. And so this is a manifestation of the ability that Wiesner found, where the reading of a message will destroy the message if it's written in a set of states that you hadn't expected to appear there, or if it's written in too many states. And it's this fundamental limitation that gives rise to the possibility of quantum cryptography. I'm going to take a drink of water here. But before I get to that, I'll use just bring up a pedagogic analogy to this strange behavior of quantum systems. You might say it's one of the most fundamental strangenesses that come out of quantum mechanics. And it was suggested by my longtime collaborator, Bill Wooters. And he says it's a little bit like the old-fashioned kind of school where the teacher asks the questions and expects the pupils to answer them, and not to ask questions of their own or to volunteer extraneous information. And he says in this analogy, the photons are like the students, and the measuring apparatus is like the teacher. So the teacher says, "Is your photon, is your polarization vertical or horizontal?" And the student says, "I'm polarized at about a 55 degree angle." "I believe I asked you a question. Are you vertical or horizontal?" "Horizontal, sir." "Did you ever have any other polarization?" "No, sir. I was always horizontal." So this behavior is something that people try to get around, but there's no way of getting around it because it's mathematically part of a consistent whole, which I will explain a little bit more without using too much mathematics. And in particular, it's not possible in principle to determine the polarization of a single photon if you don't know what it is beforehand, and to measure that angle with any degree of exactness. The best that you can do is measure it along two perpendicular axes, and it might behave probabilistically if the two axes that you chose didn't include the direction it had originally. And another thing that comes out of this is that it's impossible to clone photons, take one photon and make many copies of the same kind. Now, that seems a little strange because we are all the time using a photon cloning device in our technology, which is a laser. And a laser is exactly a photon cloning device, but it works well only if the input signal to it is sufficiently large. And in principle, a laser in which you try to send in a single photon, it will sometimes amplify it and make two copies of the same photon. But equally often, it will fail to copy it and instead emit a random photon. This is called spontaneous emission. And so this combination is brighter, but noisier, and therefore no more useful in figuring out what the original photon's polarization was than if you hadn't tried to amplify it. So now these things were first put to practical use by Wiesner in his manuscript that he wrote in 1968 and eventually got published in 1983. And one of his applications was quantum money, where and this is something that couldn't be made in practice even today, or you could make it, but it would have a very short half-life so that it would last long enough. Maybe you could use it in a country with very rapid inflation. But anyway, imagine that you have 20 perfectly reflective boxes, and you put into each one a single photon of one of those 4 polarizations. And the bank knows, or the mint where the money was made knows what those polarizations are and keeps a record of it along with the serial number of the banknote. And then if somebody tries to counterfeit it, they won't be able to measure all of those 20 exactly, and so that with high probability, when they pass their forged banknote, they'll be caught. Now, quantum cryptography, which is the sort of the first practical application of this idea, came out in 1984 or 83 actually, but the published version of it, this paper I wrote with Gilles Brassard, and this is after we wrote the paper about it, we built an apparatus, and this is clearly a piece of apparatus built by theorists. It was able to transmit quantum information over a distance of about 30 centimeters. But anyway, this paper actually came out in India, and this is a building that some of you may be able to recognize. I think this is located in Bangalore. Can somebody tell me what that, or put in the chat what this building is? Anyway, this paper came out and began in at least in some part of the information theory community to get people interested in quantum information processing. Oh, so now going back to the science of it, despite these differences from classical information, there are important similarities. And this was, people who worked in quantum mechanics didn't think of information as being like bits. They thought of it as being like physical systems and directions in space and spins and amplitudes of electric and magnetic fields. The idea of a quantum bit or a qubit came up much more recently. And so these are the parallels. Just as we know that all processing of classical information can be reduced to bits, two distinguishable states, and simple logic gates that need to act on only 1 or 2 of those at a time, and that this independence of their physical embodiment is tremendously consequential, because you can make computers smaller and smaller and faster, and they're equally valuable mathematically, but more valuable economically because you can do more with a much smaller piece of equipment. Now, similarly, we now know that quantum information is reducible to quantum bits. That is, systems that have only 2 reliably distinguishable states. As long as you have a lot of those systems and you can control the way they interact, and you can keep them from wandering away from the state they're in when you want them not to interact. And the interactions need not be complicated. You can get everything you need to do done by operating them on 1 and 2 qubits at a time. With the most exciting manifestation of quantum information is entanglement. And I'll show you how it arises naturally during interactions because of the superposition principle that I told you about before. So I said that any quantum data processing can be reduced to operating on 1 and 2 qubits at a time. So you can think of the qubits as going through a quantum computer on these lines, which a computer scientist would call wires, if you think of a wire as carrying a classical bit. And then inside the computer, some pattern of interactions take place. And the interactions are of 2 kinds. They're ones like the little box with the U on it. I think I've got right there, where a single qubit is rotated in space, in its own space. And then the other kinds of interactions are like interactions between 2 qubits, which are of the sort that you only need one of these interactions between one kind of interaction, and it's the quantum equivalent of the exclusive OR operation. In other words, if we have 2 qubits, and I'm going to color them different colors so we can keep them separate, we'll call a vertical polarization a 1 and a horizontal polarization a 0. And in using the notation that was introduced by the physicist Dirac, to indicate a quantum state, we enclose it in the half-angle bracket. So on the left, we have a control qubit, which is a 1. The green one is trying to control whether or not the target qubit, which is the orange one, whether or not it gets flipped by 90 degrees. So if the green photon is in the 1 state, the orange one is rotated by 90 degrees. If it's in the 0 state, it's not changed at all. So this is a quantum gate, and you needn't say much more about it than this because it obeys the superposition principle. And therefore, if I give it a superposition of inputs, it has to produce a superposition of outputs. And so since 2 photons of 2 different colors have 4 reliably distinguishable states, the result lives in a 4-dimensional space, and it's the state, if I control it with a diagonal photon for the green qubit, I come out with a state that's halfway in the 4-dimensional space between 2 of them, the 2 photons being horizontal and the 2 photons being vertical. So that's a well-defined direction in 4-dimensional space, but it's something that is not representable by saying that each photon has a state by itself. So in particular, this state is the same as the superposition between both being left diagonal and both being right diagonal. It is different from both of them being, say, right diagonal. So you could say that if your audience is beginning to get tired of talking about 4-dimensional space, which is the smallest number of dimensions that you could make this work in, you say, okay, I won't talk about that anymore. I'll just say the 2 photons are in a definite state of sameness of polarization, even though neither one has a polarization of its own. Well, that idea sounds like a very vague idea. And I'm old enough to have been, not quite an adolescent, I was a bit older than that. I was an impressionable 25-year-old, I guess, in 1967, which was known at the time as the Summer of Love. And the streets were full of people who were sure they were in perfect harmony with one another, even though they had no firm opinion about anything. Now, the hippies believed that if you had enough LSD, everybody could be in perfect harmony with everybody else. But now we have a quantitative theory of entanglement and quantum information. We know it's monogamous, and the more entangled 2 systems are with each other, the less entangled they can be with anything else. Now, what's entanglement good for? Bill Wooters and I and Gilles Brassard and 3 others had a really, I think, the most fun discovery of our lives when we figured out something you could do with entanglement that was really fun. I mean, it may be useful as well, but it was fun. And we faced the problem. Suppose you have a photon of unknown polarization, let's say a green photon coming in on the left, lower left, and you want to get it to another place without measuring its polarization. But you don't just send it, you want to somehow get the information out of it and then put it into another photon, which I said was not possible. But there is a way of using entanglement to make a kind of an end run around this logic. And this is how it's done. This is called quantum teleportation. And what you do, well, if you just tried to measure the photon, you would get a inaccurate result. You might have disturbed it, or you might have accidentally measured it correctly. But in any case, all you would do is prepare an approximate and maybe wrong copy. But the way we get around it is to prepare an entangled pair of particles, B and C, and then when we don't measure the photon A alone, we measure their relation between photons A and B who have never met before. So it's sort of like a blind date between photons A and B, and we don't ask them anything about themselves. We just ask them what their relation is, and so they have to choose one of 4 different kinds of relation they can have. Like whether they like each other or not, something like that. And that's 2 bits of information. And that, of course, disrupts their original state, so we can't ever find out what those were. But we take that relation, which is one of 4 possible messages, and we send it to wherever the other member of the entangled pair is, and we do one of 4 different rotations to that one, and it turns out when you do the math, it comes out, and the teleported photon is in the same state as the one that we destroyed on the lower left. And it's gotten away with this without doing anything that breaks physical laws, because it can't transmit information faster than the speed of light because it requires sending the classical message. And it can't copy it because you destroyed the original, and you had to do that before you could create the copy. So in this sense, you could say that teleportation is a way of transmitting quantum information from one place to another by separating it into two parts, one of which is classical and the other part is entanglement. That is the BC entanglement. And the part that goes via the entanglement, not only does it appear to not to behave like gravel or cement or some material commodity, it even seems to go backward in time. It seems to go from this place here. So part of the information goes this way, and the other part goes this way, but it goes through in a way that cannot be used to send messages backward in time. So that's what made this protocol fun to discover. But now this is also what made people scared of entanglement, and the cultural change that gradually gave rise to quantum information theory, which I think is now quite well accepted as a set of very fruitful ideas in other fields, as I'll mention. But when the weird behavior of these particles became evident, Niels Bohr said the physicists have to learn to live with it. And there were two kinds of weird behavior. Everybody agreed it was weird. The indeterminate behavior of a system that is prepared, even though you prepare it many times in the same state. And this is exemplified by the photons being measured. And the other thing was this entanglement, which Einstein didn't like either. And he called it spooky action at a distance. The idea that the two entangled particles are influencing each other rather than having a special kind of correlation that is not an influence, but is something that just doesn't fit with conventional ideas. And for all of his brilliance, Einstein just was never happy with this. He said, every effect should have a cause, and the cause should be nearby. And so this just felt like something that didn't make any sense to him. Well, so this is, I think, responsible for the reputation that quantum mechanics has of being incomprehensible. And I sometimes say that Einstein was so influential that his dislike for entanglement kept everybody else from thinking about it correctly, and they continued thinking of it as an influence rather than as a correlation. And since I know German, I coined a new German word, which means spooky delayed action instead of spooky action at a distance. But anyway, this turned out to be very fruitful because of several people who didn't understand entanglement thought it could be used for long-range communication. And one of them published a paper, and as I understand, the referee looked at the paper and said, "This is wrong, therefore you should publish it." And they published it, immediately gave rise to explanations of why it was wrong, and that was sort of launched the understanding of the no cloning principle of quantum mechanics, which is, and how it's a manifestation of the superposition principle that they'd known about for 30 years at the time, 50 years. But this is just another one of these ideas that's so fascinating and so appealing that it's perpetually being rediscovered. And those of us in the field get at least one suggestion every year from someone who's discovered how to use entanglement to communicate instantaneously over long distances. Okay, so that entanglement was actually grew out of another thing which Wiesner had discovered. It might or quite earlier, but he didn't get around to writing it up until a paper I wrote with him in 1992, which is using entanglement instead of to send quantum information through a classical channel to increase the amount of information that can be sent through a quantum channel. And I'll talk more about this later. So I mentioned this idea of monogamy of entanglement, the idea that entanglement, which I showed you here, you see a diagram which shows you how you have two qubits, and the Bob qubit starts in a 0 state, and we put it, for example, a 45-degree diagonal state in for Alice. And as a result of this interaction, the two become entangled. And I use this, again, this is the sort of dinner party metaphor, that it's a little bit like the social interaction between a couple who is really very much in tune with each other, and third parties, and that usually disrupts the perfection of the relation between the couple. And that's in this old saying, 2 is a couple, but 3 is a crowd. But as in human affairs, suppose we have 2 entangled systems and we just try to untangle one of them. We try to violate the monogamy of entanglement by entangling one of them with a third system. So here we say Bob says oh, I love being entangled with Alice. Let me get entangled with somebody else here. So we do the same thing over again. And Bob hopes to be entangled with both of these girlfriends. But what happens is that his relation with either one of them becomes degraded to mere correlated randomness. So in other words, they will no longer yield the same result if you measure their polarization along the same axis. No longer by measuring Alice will you know exactly how Bob would respond to the same measurement. So the strength of this magical strength of their relation has been broken. But there's even another parallel to this, which was inadvertently discovered by the writer Colette in 1929, which is even before Einstein, Podolsky, and Rosen, and the paper by Schrödinger, which mentioned entanglement. Of course, she doesn't deserve credit for this because she didn't think of it as physics. But anyway, what she found, or what she wrote about, people know this forever. If one of Bob's girlfriends leaves, his relation with the other is reduced to mere correlated randomness. But if they both stick around, he ends up perfectly entangled, not with either one, but with a now highly non-trivial relationship between the two of them, which is an appropriate punishment. So, having talked about entanglement so much, why, if it's so important, why wasn't it discovered until the 20th century? Well, because of monogamy. Most systems in nature, other than little ones, really tiny ones like photons, interact so strongly with their environment that they become entangled with it almost immediately. And because of that entanglement and the monogamy of entanglement, any previous entanglement that might have existed among the parts of the system is degraded to correlated randomness. So we look around in the world and we see nothing but correlated randomness, and we think that's all there is to information, but it all comes from the quantum nature of information. So how does this entanglement hide? And so we get quantum laws which give rise to a classical appearing world. Well, our world is not exactly in thermodynamic equilibrium. We live in a special part of the universe in which parts of our environment are continually interacting with us and then going away where they no longer interact. And this is, for example, photons from the sun coming and hitting the earth and going off into space. Now, the mathematics of entanglement, you can show that this massive, you might say it's a kind of massive eavesdropping, causes the system to be classically correlated with many parts of its environment, but it's only entangled with the whole environment. It's not entangled with any of the individual parts. And this was a phenomenon that was first pointed out by Zurich and Bloom-Kohut, and they called it quantum Darwinism. But I think quantum spam would be a better name, because the multiple copies are not copies of each other, but are copies of the same original. But of course, I was not the discoverer of this, so I don't get to name it, and they like to call it Darwinism. And this is typical of what happens in those parts of the universe that are not at thermodynamic equilibrium. And the Earth's environment is like that. So we have photons from the sun hitting things on the Earth, making them classical, and then going off into space. But if you looked at it as a quantum system, the Earth and all these photons that had ever come from the sun and gone off into space would be entangled. So they wrote, Zurich and my former postdoc, Jess Riedel, wrote a paper explaining how this, quantitatively, how this happens in everyday life in the kind of environment that we have. But if you put the Earth in an environment where you prevented this from happening, say put it in a perfectly reflective box where all the photons that come out of the Earth just get reflected back, and the whole thing comes down to a constant temperature, thermal equilibrium. I guess that would take a long time because you'd have to wait for the uranium and thorium to decay inside the Earth. But what you would then have is a system that was no longer classical, and there was and you could not. I mean, it would be a very boring place. So as I got back to this, I was saying, how do we use entanglement to understand the quantum weirdness? That is, how a system prepared the same way, a bunch of photons all polarized at the same angle, sent into the same piece of equipment to study them, they behave differently. Well, the answer is that I didn't quite tell you the truth, or I didn't tell you the whole truth when I said the photons go into this crystal and some of them become horizontal and some vertical. What really happens, well, I'll tell you what happens a little bit later. What really happens is that I'll tell you now, that they go into a superposition of being in the upper beam and horizontal and being in the lower beam and vertical. So it's not that some of them have decided to become horizontal. They haven't decided yet. They're actually both horizontal and vertical at the same time because they're really an intermediate state, but as indicated by the diagonal polarization. But this is an intermediate state on the left when they're coming in. They're intermediate in a two-dimensional space of vertical versus horizontal. But here they're intermediate in a four-dimensional space, which is horizontal and in the upper beam and vertical in the lower beam. And that means that if you don't observe them, that is, if you don't make multiple copies of that information, you can undo their random behavior. And you can do that with an optical device called a half-wave plate, which converts vertical photons to horizontal and horizontal to vertical. And then if the half-wave plate is put in there and you put another calcite crystal of the same thickness, they will forget their behavior that they never really had because you didn't look at it, and they'll come out. So if you put it in terms of that metaphor of the domineering teacher and the shy student, it's the public embarrassment of the student of having to talk in front of the whole class that makes him forget his original polarization. So taking the ordinary ideas of classical information processing, information processing, which we now call classical information, a classical bit is just a qubit that happens to be one of two chosen reliably distinguishable values that we can call 0 and 1. A classical wire is a quantum channel that conducts those faithfully, but randomizes superpositions. And that happens because when the data is passing through the wire, if it's anything but a wire that has very little interaction with its environment, like photons traveling through air, if it's almost any other kind of channel, the environment will eavesdrop on it and get a copy of it if it was vertical or horizontal, and otherwise become entangled with it. And if you lose the environment or it escapes, then it looks as if the photon has behaved randomly. So a classical channel is a quantum channel with an eavesdropper, and a classical computer is a quantum computer that's handicapped by having eavesdroppers on all its wires. So I'm now going to talk a little bit more about what Shannon did with information theory and what the quantum generalization of it is. Now, the two big formulas Shannon discovered were the formula for what he called the entropy of a source. That is how much information is in a source, and it depends on the probability of emission of the different signals summed over used to weight the logarithms of the probabilities. And it tells you how much a message can be compressed and still being able to recover it. So we use this all the time in data compression and communication and getting information out of memories. And everybody thinks of memories as something that has capacity in bits or bytes. And the other thing that he discovered, which maybe is even more important, is how much information can be sent reliably over a channel. And the formula for that was we take the maximum over sources of the difference between the joint entropy of the input and output of the channel and the sum of their two separate entropies. And that he showed that if you try to communicate through a channel at any rate less than that, then you can do it with arbitrarily high reliability. Now, back in 1997, Cerf and Adami said, well, what does this formula mean if we substitute the von Neumann entropy, which is the von Neumann's generalization of the idea of entropy that Shannon had found. And they came up with this quantity, but they didn't really understand what it was, what it meant. Well, first of all, I should say what is the quantum generalization of Shannon entropy? Well, it's given by this formula down here. I use an S instead of an H. It's the matrix analog of the Shannon formula, in which we use the trace of a density matrix. So the density matrix is the quantum generalization of a source. So it's a very straightforward generalization that was discovered well back in the 30s by von Neumann, and is full of applications in quantum statistical mechanics. But Cerf and Adami were the first people who speculated about what it meant in terms of information theory, but they didn't quite know what the answer was. But Schumacher found that a source here, imagine a source emits two kinds of signal, horizontal and diagonal, with equal probability. So it would look like its Shannon entropy is 1 bit per photon, but the photons are in two states that are not reliably distinguishable. So it actually has less information in it than a source that was emitting perpendicular polarizations. And this can be shown by the Schumacher's result, that you can operate on these using a quantum computer. You can operate on the source and squeeze all the entropy into some of the bits, throw the other ones away, and then top it up again with horizontal photons. And what comes out is an arbitrarily good approximation to what in. So it really does show that this message has a new quantum kind of redundancy. And this gave rise to the quantum version of Shannon's first formula. And the second formula, that is that you can do compression of data, not that you can do compression, that you can expand data, make it more redundant in order to make it resistant against noise. And this is familiar to everybody. The simplest error correcting code is that replicate the bit 3 times, send it through the channel, and even if one of the bits gets corrupted, you can do a majority vote at the receiving end and get the data back reliably. So the whole theory of quantum error correcting codes was developed in the 90s. And since then, it's continued a very active theory. And similarly, you can define the capacity of a quantum channel as the capacity of the best error correcting code for getting the quantum state through with arbitrarily little disturbance in the limit of a large number of uses of the channel. So as I said, what I mean by a quantum channel in general is a quantum interaction between some data, the input, and some other system, the environment, leaving in the end the output data in general will be entangled with the environment, or if you discard the environment, it will have suffered from some noise. And that can be used to model as a generalization of any classical noisy channel. Now, in thinking about quantum information, one of the nice concepts was given this name by my colleague John Smolin, and he says it's often helps to think about any probabilistic mixture of quantum states as a pure state of some larger system, and that any noisy evolution being some noiseless evolution, unitary evolution of a larger system. And he said, since you can't stop us from thinking this way, it's just an interpretation, we're going to call it the church of the larger Hilbert space. And this is an idea that is radically non-classical, because the idea that that a pure whole can have impure parts is is explicitly contradicted in the Bible, and where it says if you have part of your body that is committing a sin, you should chop it off, because the whole can be no purer than its most impure part. But going back to quantum information, leaving the Bible behind, we know that at a noisy channel, you can think of it as something that happens to a quantum state. But you can say, well, let's say what we mean by the noise is that it interacts with an environment and we maybe lose track of the environment. So we've taken the church of the larger Hilbert space and we purify the noisiness of the channel. I say purify, I don't mean we make it pure, but we embed it in something bigger that is pure. But then we can do that again and say, well, what do we mean by a noisy source? A source that might emit one thing or might emit another. Well, what we really mean is a source that was entangled in a pure state with some reference system that never even goes anywhere near our channel. So it's really a three-body way of looking at something that looks like a simple process in Shannon's way of looking at it. And it involves a evolution of pure quantum states, which you can think of as an interaction of first of all, as a state of two systems, the reference system and the quantum system, Q, and they interact, but the reference system has another part, its purification, and in the end we end up with three different subsystems that are in an entangled pure state. This is the sort of the ménage à trois of Colette. And when we think in this way, the mathematics gets a lot easier, and we can start thinking about the seeming complexity of quantum channel theory. That is that there's lots of different capacities. A classical channel has only one capacity, according to Shannon, but a quantum channel has a capacity for sending qubits, for sending classical bits. You can calculate a private capacity, which is its capacity for sending classical bits if the adversary has access to the channel's environment. So this is looking pretty complicated. But there are also ways in which it's simpler than the ordinary Shannon theory of channel capacity. But first of all, I'll talk about the ways in which it's complicated. One of the things is that there's no known simple formula, typically a single letter formula, like the fact that it's a property. If the source is emitting independent random signals uncorrelated with each other, then there's a capacity that doesn't depend, that can be calculated easily just from the properties of that one source. It's called a single letter formula. But even the classical capacity of a single letter formula, a single letter source, has no single letter formula. However, the entanglement assisted capacity of a quantum channel does have a single letter formula. I'm going to tell you about that now. Oh, but before I tell you about that, the idea that when I say entanglement assisted capacity, I'm offering to say if there was free entanglement among different parts of the world. Now, the idea of giving something away for free and making the world better is a very old idea in the social sciences. For example, the idea of free goods and services, or I guess now there's an idea that's gaining traction of guaranteed basic income. But then also these are forerunners of the hippies. That James Charles Fourier, who has not the Fourier analysis and Fourier series, a different Fourier. Here he is. He doesn't look like he would be very happy in a world with free love. But anyway, he was an advocate of that. And then we had the idea of free LSD. That didn't go very well either. This looked like a really good idea. Free internet information should be free. Free classical communication, that the ability to take information in one part of the world and send it to anyone who wanted it. Well, it seems to have produced a lot of fake news, and it still doesn't give us a simple formula for the quantum capacities. Well, finally, the best idea, which was suggested, at least he gave the name for it in 2001. Free entanglement. What if you say, let's simplify the world by giving free entanglement between all the senders and receivers, whatever they want to use for entanglement. We know this is no good for sending messages from one place to another, because otherwise we'd be communicating faster than the speed of light, but maybe it will, and it does. It simplifies the theory of channel capacities in a way that would have amused Shannon. And this is how it did it. Oh, I should say another way in which classical laws are simpler is the universality of interaction. And that is, in classical communication, there are different kinds of interaction that are not substitutable for one another. For example, as if I'm a speaker and you're a member of my audience, like what's happening right now, no amount of talking by me enables me to ask you a question, or you to ask me a question. So in other words, my speaking and your asking are incompatible resources. No amount of one can be used to substitute for the other. But quantumly, interactions are intrinsically bidirectional, and there's only one kind of interaction in the sense that any interaction can be used to simulate any other. Okay, well, now I'm going to go back to what I meant by entanglement-assisted capacity. So if we take our noisy channel in this orange here, where we have there, and we say, well, let's go to the church of the larger Hilbert state. So this noisy channel really is the noisy source was actually a pure state of which we've kept the other part and don't let it go through the channel. And the channel itself is an interaction with an environment. So there's an environment which I haven't shown you here that comes into the channel in a zero state and goes out in some state that's entangled with the other two parts of the system. And so the entanglement assisted capacity then is the maximum. It can be shown that it's the maximum over the sources of the von Neumann entropy of the input plus the von Neumann entropy of the output minus this thing, which is the von Neumann entropy of the joint system of the input and what essentially was a copy of the output and what was a copy of the input. The output isn't there anymore because it went through the channel and you can't copy quantum information. So this is exactly the formula that Shannon discovered, except with in our papers that we wrote about it here with Peter Shor, John Smolin, and Ashish Taplial. And Holeva also wrote about it in 2001. So what Shannon discovered was an elegantly simple formula for entanglement-assisted capacity, except for the channels he was thinking about, it happens to be the same as the ordinary classical capacity. So this is a case where the assisted capacity is conceptually simpler and has a simpler formula than what seems like the straightforward idea of how much can you send through without assistance. Now, this led me to, at one point, to some very grand speculation, because one of the things that we discovered was that entanglement can boost the capacity of a classical channel. Entanglement is no good for communicating by itself, but if you have a noisy classical channel, even one with very low capacity, you can use it for sending more classical information than you could have if you didn't have entanglement. And so we said, oh, well, that's got to be very useful. Maybe you can use it for communicating with spacecraft, because we have this low capacity channel we're trying to communicate to spacecraft off Jupiter somewhere. Maybe we can pack it full of entangled particles that are entangled with particles we still have on the Earth and communicate it with a much higher rate. Well, that turned out to be an idea that didn't work. The kind of channels in which there is a very large enhancement of capacity due to entanglement is channels with very high noise but low loss. But the ones that you use for communicating with spacecraft are the opposite. They have high loss and low noise. So I myself experienced a channel with low loss and high noise in one of the last conferences that was held in person in the subject of information theory. And this was held, ironically, for a room full of information theorists. They held the banquet in a room with very poor acoustics. It was very large, had very many people talking in it, and very reflective, reverberant walls. So as a result, everybody talked louder in order to be heard. But that actually made it harder for anybody to hear anyone else. And while I was there, I took a picture of my wife who was talking to the bartender trying to get a drink. But everybody was having to yell in there. And you should think that information theorists, if they ran a conference, they would worry about that kind of thing, but somehow they missed this. And here we are, they're trying to talk and everybody's talking as loud as they can, definitely not 2 meters apart. And this would give everyone nowadays a scare, like what, this is a super spreader event. But of course, at the time, this is 2019, we didn't know about it yet. So this is an idea that never went anywhere. That is to use entanglement to boost the capacity of a classical channel in a useful setting. And all these strange behaviors come from this thing that I mentioned before, that was the violation of the biblical principle that as a whole cannot be less random than any of its parts. So you can naturally imagine the entropy of the joint system minus the entropy of the part as the amount of information that the part tells about the whole. And that can, at most, B can tell us nothing about AB. It cannot possibly take away what we know about AB. It makes no sense. But in quantum information, the part can be less random than, the part can be more random than the whole. And one of my, so this is, so in other ways in which information behaves differently from stuff is the idea of trying to communicate nothing. Now that's actually quite difficult. And very often politicians try to communicate nothing and they end up accidentally communicating something. Now, my best example of this is not a politician, but it was some employees in the airport. Dave, do you remember airports? Anyway, we used to have airports. And in the airport in Frankfurt, one of the world's busiest airports, there's a place where you wander past and it's a very confusing part of the airport. So people go over and start asking anybody they can see for information, like where do I go to get to Terminal C or something like that. Well, it turns out the people who are working there are not, that's not their job to give information. They've got something else to do and their desks just happen to be in a bad place where everybody asks them questions. So one of them put a sign on their desk saying no information, and in an effort to prevent people from asking them questions. And yet when you say no information, it cannot avoid but communicate information. So getting back to this idea of negative information, or so how a part can be less random than the whole. One of my colleagues, Andreas Winter, tried to explain this to a journalist, and I think the result was a better illustration of negative communication than he could have hoped, because this is what came out the next day in the paper. Scientist knows less than nothing. Well, now I'm going to go back to the other discovery of Wiesner, and that is the idea of getting a message where where you can send a message, but reading it one way spoils your ability to read it the other way. So, one of the applications of one of the first applications of quantum information was quantum cryptography, and that was where Alice and Bob communicate over a noisy channel, and Bresard and I and our students built this clunky demonstration of it, and now it occurs over thousands of kilometers with satellites and so on. But the idea is you have two parties who trust each other, and then one eavesdropper who's trying to listen to their communication, and they're able to defeat her using quantum cryptography. But often in the business world especially, and maybe even more even nowadays in diplomacy, we have people who are trying to cooperate even though they don't trust each other. So instead of having two good guys and one bad guy, you have two good guys who don't trust each other. And but they wish to cooperate. They want to be able to make decisions as well as if they were dealing with a trusted intermediary. So this is an important practical problem. And who do they hire for that job? Of course, they don't trust anybody. So there's nobody who can be a trusted intermediary. Well, it turned out that this task could be accomplished if you used one of the other things that Wiesner had invented, the idea of a channel in which you send a message through it. You combine two messages and you somehow send it through it in such a way that when it gets to the other side, the receiver can receive either message reliably but can't get both. And so this idea was independently discovered by cryptographers and shown to be extremely useful for this important task of discrete negotiation between mutually distrustful parties. Now, meanwhile, something that was foreshadowed even by Wiesner and worked out in detail by Myers and Low and Chow, that's this multiplex channel and all such schemes can be broken in principle if you have an adversary with a quantum computer who is able to store quantum information for an unlimited time. But we don't have that now. So until there is really good quantum computers and quantum memory, we have a kind of quantum security that is entirely different from the classical computational security people use in things like what they call, I'm trying to think of the word for it, homomorphic encryption, as a way of allowing your data processing to be done by somebody you don't trust, but encrypting the input and output in such a way that you know they've done the job, but they haven't learned anything about your data. So this is in widespread use and other manifestations of it, like public key cryptography. But it all depends on mathematical assumption, and instead you can substitute a physical assumption that is your adversary doesn't have a really good quantum computer or a really good quantum memory. So this is another area in which there's practical application. But now I'm going to go back to theory and say, what has information processing, not so much the information theory, that is the communication and storage theory, but the theory of computing. And the landmark there was the discovery of universal computers by Turing, and the dual and necessarily concomitant discovery that certain problems having to do with computers' behavior are intrinsically unsolvable. This is called the unsolvability of the halting problem. And there's been a Turing and in the immediate people after him, Church and Kleene and developed a whole theory, which was at that time called recursive function theory or computability theory, of what you could do with Turing machines or with computers in principle if you had unlimited time and unlimited memory. And they began to discover classes like the computable functions, the problems that were equivalent to the halting problem. These are problems where if the answer is yes and you wait long enough, you find out. But if you don't, if you get tired of waiting, you don't know whether the answer was yes or no. And then they have found large hierarchies of higher and higher computable problems. That is the next category up was, suppose you had an oracle for solving the unsolvable halting problem. Well, then Turing showed that this enhanced computer's halting problem would still be unsolvable. So there's an infinite hierarchy of those things. Well, there was some hope initially that quantum computers could solve the halting problem, but this is not so. They have shown to be the same class of computable functions as for classical computers. So at that point, the theory of computability, the fashionable part of it and the part where progress was being made, was not so much computability or not, but what they call computational complexity. In other words, the difficulty of performing a computation in terms of how much time or memory it would take. And so we, instead of these computable and then a hierarchy of uncomputable problems above it, we have hierarchies that are sort of similar, where we get these well-known classes like computable with random assistance, non-deterministic polynomial time, and a lot of discoveries that have happened in that field. And now, since the 90s, there's the theory. Well, how does a quantum computer change the difficulty of computation? And so, what are the computations that can be proven to be hard for a classical computer but easy for a quantum computer? Well, just last year was a really unexpected result connecting these two fields, that is computation theory and information theory, that had sort of drifted apart into their own separate projects. And that was to show that one of the well-known, at least well-known among computational complexity theory classes, which is called MIP star. That is two interacting provers who know the answer to a question and communicate separately with somebody they're trying to convince, but not with each other. But they have entanglement, and that's what the star is. And if they're trying to convince somebody of something, what can they convince them of? And it turned out that it was exactly the problems that were equivalent to halting problems of a Turing machine. So these two separate branches of information and computation theory that appear to have been branches of very practical, but essentially mathematical ideas. Once you brought in an additional mathematical idea from physics, that is superposition and entanglement, it turned out that you got a beautiful simplicity in some of the deepest questions in those two fields that seem to be separate. So this is my last slide, and I think that the lesson from this is that quantum information is information. It's the right way of thinking about information. It's the coherent way of thinking about communication, computing, and interaction, in which classical behavior is clear how it emerges as a special case. And a classical communication is just a kind of handicapped quantum channel, one that has an eavesdropper. Classical computer is a quantum computer handicapped by eavesdropping. And unexpected properties of information owing to its quantum nature are still being discovered. And so that's why I think, and why I try to explain some of this stuff in a way that's intelligible over a dinner party without a blackboard or PowerPoint. And that like the roundness of the earth or the fact that matter is made of atoms, quantum information is something that everybody should understand. Oh no, so they go around saying, oh, that's sort of like entanglement, isn't it? We haven't gotten there yet, but I think we should go there. It should become part of a general education. And thank you for your attention. And if there's any medium here for somebody to send me questions that people have submitted, I'm here to answer them.
Thank you very much for this very, very engaging talk. I think we are clapping. I think some people are also clapping. Did you hear that? Okay. So thanks a lot. That was wonderful. Yeah. So yeah, we are open for questions. Well, we have a chat, and then so I'll just read out. So thank you, Dr. Bennett. I really enjoyed your content and humor. I study quantum cryptography, and your talk was great for presenting old ideas in new ways. This is Kim in the audience. So any further questions, comments?
I like the idea of presenting old ideas, old ideas in new ways,
right,
or new ideas in old ways. Yeah, they're both useful.
Yes. Any comments from anyone? We do have around 150 people still remaining. So at a moment, at some point, we reached 230 is what we noted. So we did well. Yeah. So does anyone have any questions, comments? I can see Lev with his camera on. Was that with the intention of saying something? Because
if you want, I'll go around and look for other people.
I can see his camera on. Yeah.
Oh, that sounds like Lev.
Yes. Just a small comment about something which you was talking in the beginning. You said that if you'll put a mirror around Earth, then we'll come to equilibrium. Which this is kind of, if we wait long enough, we'll come to the same state. So we'll come to equilibrium for some time. What do you mean? What was the meaning of this? When the closed system do not come exactly to equilibrium, or they come to equilibrium for some time, or
yes,
can
what
you
I mean,
expand
yes,
on this issue?
yes. If you take the Earth or any system that has got a sufficiently complicated Hamiltonian, and you cut it off from the environment, so it only interacts with itself, like putting these mirrors on it, then of course, in one way of thinking of it, its pure state will evolve according to the Hamiltonian. But the trajectory of this pure state in Hilbert space will pass almost all the time in a heavily entangled state in which any subsystem smaller than half the total size looks to be in a mixed state. So it's just sort of saying that you're exploring sort of the energy surface, what would be like the energy surface in a classical phase space. You're wandering around in a very big Hilbert space, of which almost all the states in there are heavily entangled. And if you view any small subsystem, it looks like it's almost all the time in thermal equilibrium. That's what I meant.
Okay, we have a question from Apurva Patel. There is a fundamental conflict between superposition, which is linear, and gravity, which is non-linear. That may be relevant to the measurement problem. What are your thoughts on it?
Well, we're getting now into interpretations of quantum mechanics, and I certainly agree that combining superposition with gravitation theory is the outstanding problem of physics. So I don't know how that will be resolved, but my philosophy on the measurement problem is that the mysteries, much of the mysteries of the quantum measurement problem can be understood in terms of decoherence theory. In other words, the unitary evolution of the whole. And so of course, when you try to explain the arrow of time, you have the same kind of problem that people have struggled with for 150 years, of explaining why we're in a world that allows us even to do science, because it's out of equilibrium. And quantum mechanics doesn't help answer that. Probably the answer comes from gravity, but I don't think specifically the measurement problem, in the sense that that gravitation is responsible for the collapse, not of black holes, but of the collapse of the state when you measure a quantum system and it decides to be in one state or the other. I think that is a consequence of entanglement with an environment which is too, so in principle, there's no collapse. It's just that the information gets entangled among too many systems for us to handle. And I think there's been no experimental evidence that there is a size beyond which you can't apply the idea of unitary evolution. But of course, the frontier of that is exactly in the field of black hole information problem.
There's a question from Akash. Is there a way to determine how long an entangled state under the influence of high decoherence is going to stay entangled?
Yeah, I think that I think it works out as sort of a double exponential of the number of particles in the system. It's a very long time. If you just take billiard balls in a box and say, how long do you have to wait for them all to go over to the one half of the box, it grows exponentially with the number of billiard balls. And I think it's worse if they're quantum.
Then we have a question from Abhishek. Is entanglement-based QKD necessarily more secure than faint laser source QKD?
Well, faint laser source QKD, if you use it with these decoy state ideas, is really equivalent to a sort of a virtual entanglement way of thinking of it. There may be practical advantages, because you may be able to get entangled states that are purer than and stronger than the weak coherent state that you need to use. Or I would say the main virtue of it will eventually be when you can store entanglement, because then if I try to store a classical cryptographic key, I have to worry about somebody coming in the middle of the night and reading it. But if I store some entanglement that I have shared beforehand with a party I wish to communicate with, I can test the entanglement for whether it's been corrupted. All I need is some public communication. And then if I find it hasn't been corrupted, I can use it to send a secret message over a classical channel. So it's like a one-time pad key, except that you have confidence that nobody has looked at it when you were out of the office.
So we have a question from Rishabh. In quantum mechanics, the state of a quantum particle can only be known if the ensemble of the particle is measured. However, in QKD, we assign bit values based on determination of the state by measuring a single quantum particle at each instance. Why is this not paradoxical?
Well, because the way in ordinary quantum mechanics, that when the first part of that question was that the quantum state can be determined only by measuring an ensemble, and that is true. But you can prepare a quantum state.
Mm-hmm.
So, for example, if you have an entangled source that emits entangled photons, and you detect one of the photons in a particular polarization, you know that the other photon has been emitted, and you know what its polarization was or will be. So essentially, you have prepared the state rather than somebody gives you a state. And it's true, if somebody gives you a quantum system, a photon, and says, what's its polarization, you can't find out. But that's a different question from, can I make a system whose polarization I know? So that's essentially how there's no paradox. Preparing a system in a definite state is, in principle, can be done reliably, but that's different from taking a system that somebody gives to me and finding out what state it's in without having a promise of additional copies of the same state that I can make repeated measurements on.
We have a question from Pratik. I'm a bit confused. I mean, he's a bit confused on how 2-qubit gates work without collapsing any of the qubits.
Well, these physically how they work is it's a little tricky. That's why it's much harder to build a quantum computer than to do quantum cryptography. But in principle, you can get interactions between atoms, polarized states of atoms, such that you and this is the genius of the first people who started thinking about how to build a quantum computer with atomic physics, where you use separate degrees of freedom. For example, I'll just take a good example would be the ion trap kind of quantum computer, where you have atomic states of an ion, which are evolved pretty reliably according to a Hamiltonian. But then if you treat it with a certain laser pulse of a certain duration, you get an entanglement between the internal state of the atom and the vibrational state of the row of atoms. And this is not a measurement. This is just a rotation of this, in principle, a reversible rotation of the state in a larger Hilbert space. So some of these reversible evolutions of coupled systems, if they can be well enough controlled, do perform quantum gates that correspond to things like the exclusive OR gate.
Right. So I don't see any more open questions. Oh, okay, there's one more. For weak coherent pulse-based QKD, random number generation based on PRBS is sufficient enough for security?
Based on what?
PRBS.
What does that stand for?
What is PRBS?
Pseudo-random binary sequence.
Pseudo-random, yeah.
No, no, I don't think so, because you should use physical randomness. That's a whole other talk. You ask if you think you have a secure quantum system, ask Vadim Makarov about it, and he will explain to you why it's not secure. Anyway, no, you should use physical random number generators, and you should make sure that the physical random number generators you're using don't leak their information over. They're generating over a covert channel that might be heard by the eavesdropper, and that they can't be surreptitiously controlled by your adversary either.
There's a question about what is your physical intuition about non-classicality of entangled states?
What's my intuition? I think entanglement is what? My intuition?
Yeah, about non-classical.
I think learning to think about entanglement and to love it helps you understand these states. So that's why I'm saying eventually, and I think even Feynman, one of the famous things he said is that this was almost as influential in a negative direction as Einstein's dislike of quantum mechanics. When he says, I think it can safely be said that nobody understands quantum mechanics. So then they say, well, if Einstein didn't like it and Feynman, who knew more about it than anybody else, thinks that nobody can understand it, well, then how can I understand it? But I think Feynman probably was also hoping, and I think if you look at the larger context of that quote from him, it says in time, people will understand it and they will have an intuitive understanding of it.
Right. There's one question from Yon Suk Lee. Quantum technologies have been transferred to industry. And in fact, there are many startup companies for quantum computers as well as communications. How do you see the prospect, the future of quantum information science? And do you have any comments on the role of quantum scientists?
The role of quantum scientists? Yeah. Oh, well, of course, I work for one of these companies. So I would, fortunately, I'm not in the part of that company that is usually responsible for providing reliable answers about the future of the technology. So I don't get asked very often. And when I say where will it be in 20 years, I don't know. And
right. Okay, so I think Professor Home has raised his hand. Professor Dipankar Home, you've raised your hand. You wanted to say something? Professor Home, are you with us? Oh, it's just your hand. Yes, he is here and not here at the same time.
Hey, yes,
okay, no, he is here.
Yes,
okay, great.
Yes,
okay.
Yes.
You collapsed a superposition.
Yes, so Charles, it was a nice.
You entangled him with Lev. Okay, go ahead.
Yes, so Charles, very nice seeing you. And
yes,
it was a nice talk. I am very particularly interested about your remark about quantum Darwinism, that part you mentioned, and then you talked about briefly about it, and what is its possible wider meaning in the wider impact it can have on the meaning of quantum information. Do you have any ideas and suggestions?
Well, I think it's not intended as a way of understanding the meaning of quantum information. It's one of the ways of talking about decoherence theory. See, if decoherence talks about the relation between a quantum system and its environment, and quantum Darwinism says, well, we're not talking about a general interaction between a system and its environment, but an interaction between a system and a special kind of environment, which consists of many parts that don't interact much with each other, but interact with the system in a commuting fashion. And so that is the kind of situation where information ends up looking classical, even though it's fundamentally quantum. So it's I find it as a rather not complete, but a rather satisfying explanation of why the world looks so classical, or at least the world that we see.
Okay.
In contrast to the world where this hypothetical world of the world that's gone to thermal equilibrium and everybody's dead except for fluctuations inside a mirror box.
Okay. So it's a way, it could provide a way of looking at why in the macroscopic world we see classical information.
Exactly. That's what its goal is. Yeah.
Okay.
I think Lev has raised his hand as well. Lev Weidman.
It was more or less clear for me what you will say about my first question, but the second one, you twice said that the coherence kind of help us to see things classical, and I really don't understand it. I believe that if environment will not be, if somehow we'll use some super intelligence which will prevent environment for recording where the classical objects are, I don't understand why my experience will be different. Of course, in laboratory, the coherence is very important when if I see or do not see interference. But if I'm talking about macroscopic objects, anyways, they cannot interfere. We don't have technology for this. So why do we need environment? Why do we need the coherence with environment to see classicality? Classicality, all what we need for classicality is that we cannot interfere. So I don't think that environment is needed for the coherence. Maybe it's too, I'm sorry, maybe it's too specialized question. I would like to hear your reaction.
Yeah, you could say, I mean, this is a little bit like the two explanations of the origin of irreversibility in classical mechanics from reversible microscopic laws. And one of them is to say there's chaos and the whole system is reversible, but it's just impractical to follow those trajectories. And the other one, I think I've heard it was first expressed by Borel, the mathematician, saying that if there is a very small influence from remote parts of the environment, such as the weather on Jupiter, exerting a tidal force on the motion of atoms in a box of gas in the Earth, that if you don't know what the weather in Jupiter is, after a few seconds, the trajectories of these colliding atoms have become blurred out. So absolutely, the state of the subsystem has randomized, even though the state of the whole, including Jupiter, is still has no more entropy than it had in the beginning. So I think those are just two different ways of talking about the same thing. One is to say it's in principle, the whole universe is evolving reversibly, but we can't get our hands on all of it. And the other one is to say, or sort of the coarse-grained experience, that if you admit that we can only make approximate measurements, then even a deterministic reversible evolution looks as if it's increasing entropy. Of course, for a long time, and then we'll have a fluctuation and go back to the low entropy state.
Just maybe press a little more. You said that there are two ways, the first way and the second way. The second way is the coherence. But you say that even with the first way, even there is no this external things which will change something, we still, it will be the same effect. So we don't need environmental decoherence. Or maybe.
Oh, when you mean in my box, the world in a box principle. That is a little bit like saying that's sort of like applying chaos theory to a classical system. Say it's a pure state. All these atoms are in this particular, they start on a rectangular grid or something like that with particular velocities, but the box is of such a form that it produces a subjectively random configuration after a short amount of time. and then that the whole trajectory will explore a lot of phase space, and it take an exponential amount of time to go back to where it was. So I think that qualitatively you have a similar phenomenon of evolution of a pure quantum state under a sufficiently complicated Hamiltonian, that it just explores such a large part of its configuration space, of which most parts in terms of variables of subsystems, of weakly interacting subsystems, look like random, as if they're random, even though the whole state is an entangled pure state of the whole thing that still has zero entropy.
Thank you.
Okay, so I think we don't have any further questions in the chat window. I think they have been more or less dealt with. And so just one question I had, because, when you gave this bio, so you said about quantum information and its application to cosmology. I was wondering what exactly you're working on.
Oh, I was afraid somebody was going to ask me that.
Yeah.
The thing is, this is a very hot field because it seems to be giving insights into the black hole information paradox, like what one of the more recent developments is the question of whether there is a contradiction, it's called the firewall problem, between the idea that something falling into a black hole if you have an old black hole that has become entangled with the Hawking radiation that's already emitted, and you fall into it, does something funny happen to you? Or is it explained by saying that the inside and the outside of the black hole are not independent, and it's like saying that, do you have a violation of no cloning? That's what it looked like. There was a violation of no cloning. I think the consensus is emerging, or maybe there's several consensuses. I should say this is a field I'm very curious about, but since I never took a course in general relativity, my hope is not to make any worthwhile discoveries in the field, but merely to understand it better. And I believe that I was at a conference a few years ago in the Harish Chandra Institute in Allahabad. And there were real experts on that subject there. And I think that there probably still are. And there are cosmologists who've thought a long time about this and the black hole information problem, and a lot of them have made it their job to understand quantum information theory better in order to help solve this problem. But probably its ultimate solution will be tied up with the quantum gravity problem.
Okay, so I think there are no further pressing questions. Maybe, okay, Deep, thank you, Professor Bennett, and for holding this amazing session on the birth of the World Quantum Day, surely. Yeah, I mean, I would echo that sentiment. So thanks a lot. I think we can, formally end the colloquium now, because it's getting close to 2 hours and you will have to have your lunch. So yeah, somebody is definitely enthusiastic about the clapping.
I'll make a little final remark here.
Please.
My final remark here is that I'm grateful to my host here, Rabasi, because if she waited for them to be no questions, and there was one instant in which there was no questions, and yet she asked yet another one, and I thought, boy, if she has to wait for there to be again no questions, it may be like a Poincare recurrence. It may be not 1 hour, but 1 century with an audience this size.
Yes. And so we want to end it before midnight for us, and and because the topic is interesting enough, that we could just go on, but then I think we'll give you a break for now. So thanks a lot for your time. Yeah.
Thank you all.
Thank you. Yeah. See you then. Bye.